Thanks, Pablo. It sounds like, as usual, DREAM is always working and cooking up new and exciting things, and it's exciting to be here. And hey, thank you for inviting me. Today, I'm presenting on behalf of the CODA TB Challenge organizers, and I'm going to talk about our challenge in which we developed or worked to develop a diagnostic for tuberculosis using cough audio recordings. And as Pablo said, it's a new data type for DREAM, and so we were pleased to be embraced by the DREAM community, and excited to see the participation. So tuberculosis is a communicable disease. It's caused by a bacteria, which commonly infects the lungs, but also other places in the body. Because of that, cough is a common symptom. Importantly, prior to the COVID pandemic in 2020, it was the leading cause of death worldwide from an infectious agent. It disproportionately affects people in low middle income countries, the global south. And because of that, oftentimes there's a barrier in people getting treatment and diagnosis and treatment, which is why, this challenge is so important. So some statistics are in 2021, there were an estimated 10.6 million new infections and 1.6 million deaths. Those are an estimate because about 40% of, it's estimated that about 40% of cases don't get diagnosed and don't get treated because of barriers getting care, or when participants do get to medical facilities, sometimes the facilities are ill-equipped to diagnose them. And so for this reason, non-invasive digital screening instruments, such as those that can be deployed on an easy smartphone, easily available smartphone, can reduce some of these barriers. And as I said, because cough is a very common symptom of tuberculosis, we focused on cough sounds as a potential screening biomarker. So to test our hypothesis, we used data from 2 different cohorts across 7 different countries: the R2D2 network data from South Africa, Uganda, India, Vietnam, and the Philippines, and the University of Montreal cohort from Madagascar and Tanzania. 7 different countries, 2 different cohorts, but they all used a common protocol. So adults 18 and over were recruited from participating medical facilities if they presented with new or worsening cough over 2 weeks. And so these are the people that should have been screened for tuberculosis anyway. These are the people that, have, high potential for tuberculosis being the cause of their cough. And so they were recruited into the study. They underwent routine demographic and clinical data collection for like age, sex, vitals, anthropomorphics, and self-reported symptoms and self-reported past history of TB. They then underwent standard TB testing as they would have normally, using sputum expert and culture testing. And then the different part of this protocol than they would normally go through is that we then collected the audio coughs, or the study investigators collected the audio coughs on the HIFE research app. You can see a little screenshot of that guy. Oh, I guess my pointer is not showing up. You can see the little screenshot of the app right there, and the little stand setup where you see the smartphone on the stand. Participants are prompted to cough voluntarily. So 1, 2, 3, cough. I don't think they were covering their mouths. I just don't want to be spreading germs up here. But the coughs are then recorded by the app. You can see the little diagram of the cough up there. Coughs are then trimmed to half-second recordings. So it's also important to note that while we aimed for 5 solicited coughs, sometimes when you have a cough and you someone asks you to cough, it'll induce a coughing fit. So we, on average, did have more than 5 coughs per participant. We developed 2 sub-challenges. The first was to predict TB status from cough recordings only, so just those half-second cough recordings. And the second was to also include clinical and demographic information. And so this is, these are data that would be collected on screening. Typically, they're easy to collect, like anthropomorphics and vitals and self-reported questions. We did have data on things like HIV status and things like that. We did not include those because those typically require more testing. And so these are all very easy screening and triage sort of variables. The ones we included were age, sex, height and weight, heart rate, temperature, and then self-reported variables, smoking in the last week, duration of cough, prior TB, whether they had prior TB or not, and the type, either pulmonary or extrapulmonary, hemoptysis, which is coughing up of blood, fever, night sweats, and weight loss. Those are all common symptoms of tuberculosis. For our evaluation metric, we used the 2-way partial area under the curve with 80% sensitivity and 60% specificity. The reasoning behind this is that we weren't really interested in the full ROC curve, just sort of the clinically relevant or the clinically actionable portion of it. The WHO sets standards of 90% sensitivity and 70% specificity. We wanted to roll that back a little bit because we didn't know if any of the models would hit that benchmark, so we were a little bit more permissive with our cutoffs. And in the event that no models met the 80-60 sensitivity specificity mark, we used the total area under the curve as our benchmark. The data sets were split into training, test, and leaderboard partitions. The training partition consisted of about 1,000 participants and close to 10,000 solicited cough recordings. We also, of course, released the demographic and clinical variables, those 14 that I listed on the previous slide, and TB diagnosis. Obviously, that's our label. And for those who are TB enthusiasts, we used the microbiologic reference standard as the diagnosis. We also provided participants with over 700,000 what we called longitudinal coughs. So one thing I didn't mention about the study protocol is that some of the participants were sent home with a smartphone running the Hive app, and they wore it around their neck. It collected coughs as they went about their daily lives. So those are what we consider the longitudinal coughs, but those wouldn't be appropriate for a diagnostic. The diagnostic is coming into the clinic and coughing into the smartphone. So we're using those solicited coughs, as our metrics or as our data in the challenge, but we provided the extra longitudinal coughs as extra data to participants in case it was useful for training their model. So the test and leaderboard partitions were about 800 study participants and about 250 study participants, respectively. We used a model to data approach for this challenge, a model to data, not a model to data approach for the application of the model. Participants were still free to download the training data and use it locally, build their models, and then submit their models to us for application against the test data. So we held the test data out. We did not release any of the solicited coughs or the clinical data. The models were applied to data that were held behind our firewall. The models were applied to those data and scored against the labels. Another feature of this challenge that I think is new to DREAM is that we asked that models be submitted in ONYX format. ONYX is a method to serialize models so that they can be applied in a framework independent of the framework that they were trained upon. So it makes models a little bit more portable, a little bit more rerunnable, reproducible in the rerunnable sense. So it doesn't guarantee that you can rebuild those models, but it does make it easier to rerun them, if you want to apply them to new data down the road. I should also say that ONYX has hook-ins to R, Python. It can be applied to more traditional machine learning approaches like random forests, as well as deep learning. So it's a pretty flexible framework. This is our challenge timeline. We launched about a year ago and ran 5 leaderboard rounds from November of last year to February of this year. We had final evaluations at the beginning of February and announced the results in March. And without further ado, we'll get to the results. So for sub-challenge 1, we got 13 submissions, 11 of which completed the full set of requirements, including write-ups and code. The 2 that didn't are shown there, but they're grayed out. The top model is Blue Team, and they have a video poster later, so I highly encourage, excuse me, I'm losing my voice a bit. I highly encourage you to go see the poster video and learn about their methods later. And for those of you online, I think you can probably just stream them online. Their top model reached an AUROC of 0.74. None of the models in this challenge met the 80% sensitivity, 60% specificity benchmark. So these were all ranked based on total AUROC. Another interesting aspect of this challenge, again, you can't see my pointer, but the second ranked team is actually a high school team, a team consisting of geographically distributed high school students led by a professor, I think, in Arkansas. And so that's really cool to see, like, such young and budding minds get engaged by these challenges, and not only that, but do so well. So they'll be winning the challenges, in the next coming years. So for sub-challenge 2, we got fewer submissions. We got 8 total submissions. Again, 2 of them did not complete the full requirements, and so they're here grayed out. Of the remaining 6 models, 5 of them met the 80% sensitivity, 60% specificity mark. So so that was what was used to rank the challenges. The top team is called Metformin 121. They also have a poster video, so please go check that out. In the post-challenge, we also fit a clinical model using the same variables that the participants had, using the same training data that the participants had. That's shown here in red. You can see that the top models do outperform the clinical-only model, so that is to suggest that there is information from the audio data, but and with sub-challenge 1, we see quite good prediction from the audio data alone, but it seems like what it's adding above and beyond the clinical data is not that much. In the post-challenge, we looked at some of the variables that we had, but we did not release to participants. So we looked at the model accuracy by HIV status. And you can see that across both sub-challenges, these models are less accurate in HIV-positive participants. Granted, it's a smaller sample size, but that's important to note clinically for clinical relevance. We looked at country, which also was not disclosed to participant, country of origin of the data. This was sort of interesting because we see that there are some countries where the models perform fairly uniformly, like Vietnam and Uganda. There are others where there's very high variability among models, where some models do very well and some models do very poorly. But on average, the models are predicting in each of the countries. So that's important and good to know. To some degree, the variability is correlated with sample size, but not fully. So for example, Philippines has a pretty high sample size relative to the others, but also very high variability. So it's not exactly sample size dependent. We also looked at a semi-quantitative measure of bacterial load. So this expert semi-quant is a categorical measure from trace to very high, or from trace to high of the amount of bacteria that a study participant had. So these are only people who tested positive for tuberculosis. And when we plot the model probabilities so each set of blocks is one model, and then the box plots within the set of models is the expert semi-quant from trace to high. And you can see that the model probabilities across all models are increasing. So that's suggesting that not only are these models predicting whether or not someone has tuberculosis, but they're actually sort of predicting the burden of infection as well. And so we see that in sub-challenge 1 and on a much less busy slide, sub-challenge 2. And we again see this across all models, which is to suggest that these models are picking up sort of biological importance. So if you've listened to the talk this far and didn't participate but are wondering how you can get involved now, you can. The training data are openly available. You can go to the challenge website and request access to the data. And hot off the presses, as of yesterday, we now have continuous benchmarking. So you can also submit models to be tested against the combined test and leaderboard set. So remember, this won't be, because it's a combined test and leaderboard set, it's not apples to apples comparison to the results of the challenges, but you can go work on models and have them evaluated. And with that, there are a number of people to thank. My co-organizers from Global Health Labs, UCSF, University of Montreal, and Sage Bionetworks. The study investigators in those seven countries, the R2D2 network across South Africa, Uganda, India, Philippines, and Vietnam, and the University of Montreal investigators in Madagascar and Tanzania. And then our funding, the funding for the actual challenge was provided by Bill and Melinda Gates Foundation and Global Health Labs. And some of the data collection was funded by NIAID and the Patrick McGovern Foundation. And with that, I'm happy to take any questions.
Question for Solly. Thank you, Solly. Beautiful challenge design. I had one question. So did you see any difference between the first curve and the last one, the fifth one? I was wondering whether there was an effect maybe due to like muscles warming up and then...
That's not something that we looked at, but it's maybe something that the participants looked at. So if you have a Q&A session for the challenge winners, they might be able to tell you a little bit more about they dug into the data a little more than we did.
Thank you.
I had a question about the longitudinal cough data collection. So how did you sort of sort through just the day-to-day like background chatter and isolate these cough noises from, yeah, just other noises?
So we did not. So the question was, how did we, in the longitudinal coughs, how do you distinguish between actual coughs from background information? And so that's all part of the HIFE research app. It has an algorithm to determine whether an explosive sound is a cough or not. And using their algorithm is proprietary, but we did use the 0.85 probability cutoff using their algorithm to determine cough from something else.
Thanks.
We also looked a little bit into the coughs ourselves and fit a cough versus not cough model, and found that the results were pretty highly concordant with HIFE. So we felt pretty confident that those were actually coughs.
Thank you.
Hi, Sally.
Hey.
Just a very quick technical question. I'm really curious about this live leaderboard option. How computationally expensive are these models on average that you were running? And is that sustainable, I guess? And would that be offered for other challenges as well?
The question is, how computationally expensive are the models? And we found that they were sort of variable in terms of at least applying to new data. I don't know about training because we didn't do that, but we did have to up our instance size a little bit in the test set for a few of the models that were a little more computationally expensive. So it's possible, as this ongoing leaderboard happens, that we might have to make special changes for occasional models. But and then, sorry, what was the second part of the question?
I was curious if it's sustainable and if other challenges is this like a SAGE option that's going to be offered for other challenges. I don't know if you can
Yeah, so the question is whether it's sustainable and if it would be offered for other challenges. Jake and I have talked about it, and I know there's a good interest in doing this more often. We did get special funding, or we had a little extra funding left over, and asked if we could apply it to this. I don't know about long term whether this is going to be like regular babysitting of the queues and things like that. So I think it's a bit of an experiment, and we'll see how it goes.
Thank you for the great talk. Has there been any thought about expanding your cough collection times through direct observed therapy treatment regimes to look at how the cough changes across the treatment course for these individuals?
So the question is whether the study they were interested in following the coughs across treatment regimens, and the answer is that's sort of baked into the data, because most people who were highly suspected for having TB in these studies were sent home with therapy, and so as they were collecting these longitudinal coughs, they were also on therapy, and so that's part of the reason why we didn't use those longitudinal coughs for prediction in the challenge, because there's sort of a confounding of treatment with high likelihood of having TB. And so, presumably you're watching people with TB get better and people without TB not get better. And so that's not a good diagnostic, but that is indicative of treatment effects.
And just to follow up with that, with those individuals who wore the longitudinal phones, did they get direct observed therapy or video direct observed therapy, or were they just sent home with the regimes?
The question is whether they were observed in their therapy, and no, they were typically just sent home. Yeah.
There's an online question related to the diversity of ML methods used, or if they were more or less similar.
So the diversity of methods, they were mostly variations on a theme. So spectrograms, MEL spectrograms, MFCCs. So some variation of those was the most typical.
I actually have a question about why did you decide to do a model to data, given that you had already given the training data?
So the plan is to keep the test data held out in perpetuity, and potentially as a validation set for the WHO to validate models, that might be of clinical relevance. And so they wanted to keep that data as private as possible, and it will be continued to be held out, at least for the foreseeable future.
Just a general observation on the challenge that, a couple of things that I think were great that we see in many challenges is, for example, a team that participates very often to a lot of challenges. So like Yuan Fang Guan team. And more we're seeing these high school teams, I guess, as AI technology becomes more available, participating in the DREAM challenges. So I think that's something we should definitely push, because that's the new generation, right? Those are our next participants, as Sully was saying.
And they were highly activated. We invited them to the post challenge, and they were excited and highly motivated to be there.
And then last question is, when you I was compared to the let's say clinical assessment, right? What does it entail? Because clinical assessment, very often you need an X-ray, right? Or is it just based on, because again, there's this you want this cutoff in order for this to become, I guess, comparable, but it seems to be already doing pretty well, right, in terms of prediction, and especially in these countries where sometimes getting to a hospital is a difficult situation, right? So this seems to be something that's pretty much ready for practical use, right? Is that?
Like I said, WHO wants a 90/70 sensitivity specificity for a clinical it's a screening diagnostic like this. They would still then undergo actual testing. But in terms of should this person be screened or not, should this person undergo further testing or not, I think it's getting close, and I would defer to my colleagues who are more clinically oriented. But there is promise there.